Computational complexity, everyone's favorite topic in computer science. Computational complexity is the measurement of the amount of resources, time and or space, that a particular algorithm consumes when it runs. Big O notation is the limiting behavior. It's measuring the limited behavior, or modeling the limiting behavior of an algorithm, the order of approximation. I had to look up what the O was for big O notation. But the gist of it is, given an algorithm, let's do something like a find algorithm, right? How complex is it to implement? Spoiler, we're going to find a linear relationship to how many elements are in a collection and how long is it going to take to find those elements. Long here is a super relative term. So when we talk about computational resources, we're not talking about specifically a time-measured thing. Like, we're not saying 1 second equals one thing, 2 seconds equals two things. Like, that's not what we're doing. We're saying how many operations or how many calculations or how many memory retrievals are we doing in every step of an algorithm. So that's the important thing, is the steps of an algorithm. That's how I think about it, at least. Because it's not clock cycles, it's not time, it's a little more generic than that. But the real point of this is to compare or predict computational resources prior to execution. And I want to show you how I think about this without looking at any code, because, code. But here, let's do it with a deck of cards. If M&M's wants to sponsor me, that'd be rad. Let's say we have 4 items in my collection. I'm going to move away from a jack just to make it a little easier for translation right now. But let's say we have this collection. If we're in a computer, we've got an array or a list or a set, something like that. We're going to assume at this point that this is not sorted. Not sorted. So, if I want to find the number 8, that's easy, right? I look down, I see, ooh, number 8, done. That took me 1 unit of things. Computers aren't like that. I can look at the 4 numbers and know that I have 4 numbers. They're all in my head at one point in time. I know how to find my number. But a computer is, it may be way faster than us at doing some math. It does not behave the same way as our brain. So your brain works like they're all a bunch of inputs to some mechanism in our brain. And that mechanism in our brain has trained over the decades and millennia to be able to find something in a collection. Cool. Computers work a little differently, right? So computers, when looking through this collection, need to go step by step, right? A computer, while it may be multi-threaded, while it may be multi-process and all that good stuff, when it comes to an algorithm like this, we're always assuming, single-threaded and kind of linear operations. Meaning, if I have to find something in this, I've got to start here, look at one, look at the next, look at the next, look at the next. So if I'm a computer, really, this was my genius moment the other day. This is really what it looks like to a computer. Since the computer, in typical uses, does not have this kind of omnipresent or not omnipresent, omniscient view on these values, it can only look at one at a time. Right? So I need to find, or let's say, I need to see if the number 4 is in this collection. So how does a computer do it? Well, it's going to look at the first element, say, are you a 4? Nope. Look at the next element. Are you a 4? Yep. Cool. So I found my 4. So if I want to measure the complexity of that, I stumbled across the words limiting behavior. So a limit in math, in super simplicities, is looking for extremes, right? What's the least amount of time possible to do something, or what's the most amount of time to do something, right? So best case scenario, I'm looking for a 4. Is that a 4? No, damn it. Best case scenario, I'm looking for a 9. Is this a 9? Yes, best case scenario, one operation. Now I'm looking for a 4. I don't know where the 4 is. Well, I do now, but is that a 4? Nope. 1. Is that a 4? Nope. 2. Is this a 4? Nope. 3. Is this a 4? Yep. 4. So that took me 4 steps. Worst case scenario, right? If we add another card, worst case scenario, 5 steps. I added another 4, right? 5 steps. Are you sensing a pattern? I'm sensing a pattern. If I have to look through a collection of one element, I can tell you yes or no, this is a certain value. Yes or no in one step. This is a 6. Yes or no? No. That was an, I don't know if you could see that. That's an 8. So it's not a 6, but it took me 1 step. Now I have 2. So 1 is 1 step. 2 is this a whatever I'm looking for? Worst case, 2. Here's the pattern. 3, I have to look through all 3 worst case scenario to find that value. So this algorithm, this scan and find algorithm is linear, right? So if we drew a chart, x-axis, y-axis, number of elements, and then I'm going to put it in quotes, time, which is not really the right word, but it's what I want to use right now. I'm going to use time generically, even though it's not really time. So, if I have one element, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 to 1, 2 to 2, 3 to 3, 4 to 4, somewhere around there. We have a linear relationship. So the worst case scenario, amount of time taken to do this scan and search operation, is linearly related to the number of elements. That is expressed in big O notation like a little n. Big O, n. Where n is a representation of the number of elements in the collection. Sometimes you'll see things get worse, right? So the worse the algorithm, it might be something like that. Exponential, right? As the number of elements increase, the complexity gets, or the time, air quotes, time spent takes a lot longer. This relationship could be different. We'll talk about like a specific algorithm there, but for now, let's go back and stick with our linear. So, how does this work? Well, I showed you the cards So if I'm looking at these cards, again, to find a number, it's always a 4. I don't want duplicates, but duplicates are important. We're going to do something with duplicates in a second. That's a jack, that's a king, that's a, here we go. That's not a 4. That might be a 4. So, again, finding a 4, worst case scenario. 1 card I had to flip, and shoot, I found a 4. That's an 8. Let's find an 8. We're looking for an 8. So, I flipped first card. I flipped 1 card. Nope, not an 8. Nope, not an 8. And I'm ticking every time I do this flip. That's a 6. That's an 8. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Linear. Now, let's say I want to figure out if there are duplicates. Oh, no. Let me start over. So that was a linear relationship for time, right? The other part of this is memory usage or storage usage. And so there's an idea of constant storage usage. And then there's the idea of, I guess, I don't know what the word would be, but growing or non-constant. Yeah, we'll say non-constant, right? So now I'm going to start thinking a little more technically, because I'm using my brain for a step in here. And computers have brains and they're super smart, but a computer's brain is really broken down into 2 things, computation and memory, right? And so here I have to do something to remember if I found a number. So here, again, if I have memory, I'm going to say, okay, so I've got one piece of memory saying the number I need to look for. So one piece of memory, I need to look for the number 8. Another second piece of memory, I don't know, in a computer, it'd be like a reference to this collection, right? Or storage of this collection. And so the algorithm has its own storage separate from the collection, right? So we're really going to talk about the algorithm. So here I'm going to look for number 8. That's kind of a stupid example, but it works. Let's go for something else. Let's go for the average. If I want to find the average or the mean number of these values, I need 2 things in memory, right? Average is one of those calculations you can do in a streaming fashion, meaning I don't have to know my whole collection at one point in time to be able to calculate an average. So I need 2 pieces of thing here. Basically, I need the number of things, and then something like the sum total, or I can just keep track of the average. Depending on my algorithm, I think in the end it's all going to be the same. But let's do a sum total. That might make things a little easier. So here I have things. So when I start my algorithm, I have zeros. So I haven't looked at anything, and I don't have a sum. So let's look at our first card. So I've looked at one thing, and its sum is 9. And then I can calculate my average, right? It's the sum divided by the number of things, and in this case, it's 9. So this calculation, if I store things like this, when I'm calculating an average for every element I'm looking at, I'm really doing one operation of looking and adding. When I'm done, I can get, or really at any point in time, I can ask the computer what the average is. So this is one of those things where it's kind of overhead to the algorithm, right? No matter how many items are in the collection, no matter how big the numbers are, how small the numbers are, if they're all zeros, if they're all 12s, it doesn't matter. It's one operation, right? This is negligible. So really, it doesn't count towards, like, our big O notation is not going to be big O n plus overhead, right? Because that overhead is constant. It's constant for every time I run this algorithm. And so I'm going to kind of ignore that overhead and really big O n. So let's keep going. So I did my first one. Now I do my second one. So now I've looked at 2 cards, and now I have a sum total of 17. And so now I know if I wanted to perform this calculation at this point in time, my average is 8.5. Do another one. 3 for a sum total of 23. And I know at this point in time, if I wanted to do this calculation, my average is what? 8, almost 7 2/3. 7.666, right? That's my current average. Add another one. My fourth card. 28. Oh, good. Now I have an even average number of 7. Then I flip that card back over. I can only look at one card at any point in time. I can look at 5th and 32. So what is that? 6.4-ish. There's my average. So this took, because I had 5 cards, it took 5 units of time or units of measurement. And so these are the 2 things in memory that I stored. So really, I would call this constant memory because I'm not allocating or removing memory usage as we're going through. I'm defining it all up front. I need a number of things and I need a sum. So in my code, these will be variables, right? So I'd have an int things, not a great variable name, and int sum. Again, not a great variable name, but I have 2 variables. Those are its values. This can be calculated or stored. If I wanted to store it, because I'm looking at fractions, I'm going to have some floating point average, whatever. So I can calculate it every time. I can calculate it when I need it. That type of operation, division, is again, negligible. It is 1 cycle on a CPU, so that's really all that matters. That's a little abstraction on how it actually works, but hey, close enough. So what have we learned so far? There are certain algorithms that have a linear relationship, right? So we have linear so far. And so far we've done a scan and find. I'm saying scan and find because there's a specific way or algorithm to scan. And then things like average, sum, whatever, etc. Those are linear things. So now let's look at something a little more complex. And here's where it gets interesting. So we have 5 elements. Let's see if we can make sure you can still see those because it's going to get a little more space needy. So here, I'm going to count the number of times I do things, right? So I'm going to do I'm sorting. I should say that. So now I'm going to sort. There are bajillions, or at least 6 super popular sorting algorithms for a linear collection like an array. We're going to implement what is called the bubble sort. It is one of the least efficient sorting algorithms, but I'm going to show you this relationship. Let's do it one at a time. So I have 1. I'm going to keep a little chart over here. So when I have, so we'll say number in my collection, and then we'll say time. So for me to sort this thing, if I have 1 thing in my collection, I look at the number, it's sorted. So that took 1 thing of time. So now what happens if I put in 2? So now I have 2 items. So how do I sort this? So a bubble sort says, starting at the lowest index number, indexes are how we reference items in an array. So we'll start at index 0. This will be index 1. Whoops. Consistency, Chris. Index 1, right? So here I need to say, okay, I need to look at, I need to start from here, look through my collection to find the lowest number, and then put it at the beginning. Replace that thing. Once I do that, then I go to the second item, or the index 1, and again, starting from there, I go to the end, and I find the next lowest number, and I swap it. So that's how we're going to do this. So we're going to say, okay, that's an 8. This is a 4. So I found my lowest, and I'm going to swap it. So I know I'm swapping those. So now I'm in order, right? So let's do that again. This time we'll count. So I'll say, okay, I have an 8, so I've done one thing. And then I'm looking at the next one, and I see a 4. I've done 2 things. Then I'm swapping them. And I'm not going to count that swap, because the swap itself, in my opinion, is negligible. And so we'll kind of ignore that. So here it took me 2 times. I think it took me 2, right? 1. I looked here. That's 1. Looked here. That's 2. Swapped it. Oops, swapped it. And then, to make sure, I have to check and make sure that this is the last number, which in this case it is. I could probably shortcut it, but effectively that took me 3 times. Three checks. Okay. Now let's do it again with 3. So if I'm computer sciencing and doing index 0, 1, and 2, 0, 1, and 2, I literally have no idea what these numbers are. Let's see here. So I just did 1 check, and that's a 9. So I know, how do I keep, okay, so I know my lowest value was 9 at index 0. See, now we're starting to kind of get in the code, but not really. I have crappy memory, so I need to remember things like this. So index 0 was number 9. Okay, cool. So now that was one thing, one operation. So now let's look at the next one, and it's a 4. So is the value at index 1 lower than the value at index 0? In this case, yes. Yes, it is. So I'll say 1 is the lowest now with the value of 4. If I were programming this, I wouldn't need to keep track of the 4 itself in particular, but you know, it's not much. So I look at the next. Oh, so then that was a double check. So here I'm on my 3rd. Index 2, value is not lower, and so I'm done here. I also need to know that I'm sorting index 0, because I need to remember where I'm working from. So that took 3. That was 3 checks on the first pass. 3 checks. So that found my lowest at index 1, and I could replace it at index 0. So I swapped. I took the thing at index 0, moved it to index 1, moved the thing at index 1 back to index 0. So I'm not writing. Maybe I'm writing in Python. Maybe I'm not. So I'll need another variable for the swapping thing, but we're not really talking about code, so let's not really deal with that right now. Okay, so I did that. When I do my first pass, now I'm moving to index 1. And so far I've had 3 steps. So now this one I know is the lowest number, so I'm kind of going to ignore that, put it off to the side. So I'm doing the same thing. Okay, value at index 1, because I'm looking at starting at index 1, is number 9. So the value is 9, index is 1. That was one operation. Second operation, 8 at index 2. It is lower than the 9. So now I'm keeping that tracker there, and I'm keeping that tracker there. And here I know, so I found my lowest, and I want to put it in index 1. Again, I'm swapping these, because again, this should be my lowest number. I'm going to put it over there. So that took 2 steps. Then third, same deal, because this had to increment up to 2. This would be a 9 at 2. Took 1 step. And then I'm done. So I think that took a total of 6 steps, right? 5, yeah, so it took 6. So 3 took 6. And I'm going to do this super quick for number 4 to go through that again, just so I can kind of start this chart to show you what I'm thinking. So I'll grab my 4th card. And we'll go sort them up a little bit, or shuffle them up a little bit. We'll go here. Now again, we got index 0, 1, 2, and 3. Okay, and I'm going to start with 0, so my starting index is 0. I need a current index as well if I'm coding, but that's going to be too fine-grained, and I'm not going to write that out every time. I'll speak to that. So index 0 is an 8, so that is the lowest number I've seen so far, because I haven't seen any other numbers. Index 1 is a 4, so index 1 is lower than an 8, so that's a 4. That was 2 steps. Index 2 is a 9, not lower than a 4, but I still had to look at it. And then here we have a 3. I'm sorry, a 6 at index 3, not lower than a 4. So I know my lowest card is at index 1. So again, I'm swapping it to 0. Then I'm incrementing that, and that's going to the side. So now we'll start all over. So now we start at index 1. So I've done 3, and I've done 4. There we go. I'll keep track like that. 8 at index 1. So I know that's my lowest so far. Then I'm going to go to index 2, and I see a 9. And that's not lower than 8, so I'll go to index 3. 6 is lower than an 8. So index 3 gets a 6. Then I flip it back. Then I swap those two, and that I know is my lowest number. Okay, so now I move up to index 2 to start. And I know I'm looking at that. So 2 is a 9, 2 is a 9. Flip it back. 3 is an 8, which is lower than a 9. 3, 8. Flip it. So my lowest index is 3. Swap it. I know that's the lowest number. And then I go on to my last one, and I check my 1, 9. So it's 3, 9, 3, done. So that took me 9 things. So 4 to 9. Now let's chart this. Let's graph this a little bit. So number of elements, time, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I didn't get up to 15, but that's okay. 1, 2, 3, 4, 5, 1, 2, I only did 4, so we'll spread that one out a little bit. 1, 2, 3, 4. So 1 took 1 step. 2 took 1, 2, 3, 3 steps. 3 took 6. 4 took 10. So if I were a linear relationship, I'm just going to do a quick dot, like my 2 would be, like that would be linear. It looks sloped because my scale's not the same, but let's say that's linear. This one follows a different path. Notice that curve? And it gets steeper as we add more elements. Where's my phone? I want to oh, it's on the camera. I double checked, and this is an exponential item. And the way, well, that pen doesn't work. Okay, I double checked. This is an exponential path, because you imagine at some point in time this is going to become pretty darn near vertical. That's our limit, right? That's the whole limit. That's the worst case scenario. As things expand, we have an exponential relationship. So there is a exponential relationship between the number of items in the collection and how long it takes to perform that algorithm. So we've seen 2 different things. We've seen the O-N, linear relationship for a find or calculation, some calculations, and then we see this exponential. And this is a couple of sorting algorithms. Here I did a bubble sort because I think it's easy to show, and you can find code for it all over the internet. But we know this sorting algorithm was an exponential relationship. The reason this is important for us computer scientists, as we write software, as we build out these algorithms, it's super important to understand the constraints of the system you're in. If you have infinite CPU, then n squared doesn't matter. But we don't have infinite CPU. So we're either infinite CPU or infinite memory, but in reality we have neither. So we've got to figure out which one's our limit and which one do we stick to. If we have all the CPU in the world but super limited memory, bubble sort is super easy. If we have a lot more memory or heap or whatever, then we can do something like a merge sort or whatever. Different sorting algorithms we can talk about in the future, but for now, that's a kind of a codeless overview of complexity.